Okay, hello everyone. All right, welcome to the fifth installment of the Coding Interview Crash Course, and today we're going to be talking about trees and graphs. Okay, so here's the attendance code for those who need it, upside down. Can you guys guess why upside down is is our attendance code today? No, I mean I'll explain it later. Very very easy. Yeah, Benny, you're basically correct. But don't worry, I'll still explain it for those who haven't seen a tree before, or at least a tree in computer science. Okay, I think Arjun posted this in the chat, but here's the link if you still have if you still don't have it and you want to see the slides on your own. I'll give you guys another 5 seconds or so. All right, Bill, you want to talk about office hours for a little?
Yeah, sure. So Intro to Computer Programming, Coding Interview Crash Course is also going to host office hours next Monday, November 23rd, from 6 to 7 p.m. So we'll all be there. You can hang out with us, and we'll be there to answer questions about if you guys have any interviews coming up, we can give you advice, or you guys are preparing for a specific on-site or assessment. But yeah, come to office hours and hang out with us.
Okay, wait, I have one question.
Yeah.
Does this conflict with the event we have on the other thing we have on Monday?
That's the other thing we have on Monday.
Oh, okay. I'll message you about it.
Okay, sure.
But no, okay, yeah, I'll just message you about it. All right, let's move on to the content finally. So trees are I'd say a bit of an extension to linked list. They're an abstract data type that simulates a hierarchical tree structure. And specifically, we're going to be focusing on binary trees. So binary trees are trees where the nodes have at most 2 children. And if you guys remember what a node is from our linked list presentation, will this video be uploaded to YouTube? Yeah, it will. The last week's I'm having a bit of trouble splicing the videos, so you're gonna have to wait a little for last week's, but don't worry, I will get on that. Is there any other questions right now? Okay, all right. So if you remember our presentation on linked lists, you would remember something that looks similar to this. We'd say struct list node, it'd have some value and then a pointer to the next one, to the next linked list node. Here we actually have 2 pointers. So we have a pointer to what we call a left tree node, and a pointer to a right tree node. So if you looked at this tree, this would be the left node and this would be the right node. And then if you keep doing this, you get something that looks kind of like a hierarchical structure. I wouldn't necessarily call this a tree. Wait. Okay, all right. Sorry about that. I'm just looking in the chat. So yeah, if you continue giving each node its left and right, you'll get something that looks kind of like a hierarchy, with this being the top, which we would call the roots. And so that's what a binary search tree is I feel like I may have gone over that a little quickly. So does anyone like have any questions? Everyone's crystal clear on what a tree, binary tree looks like? Or like,
Oh, I have a small question. Why don't we use structure and not use class? I'm confused about structure and class a little bit. What's the difference?
okay, I think this is more of like a C++ implementation. I think struct and class are like interchange. Yeah, correct me if I'm wrong, but I think struct and class are interchangeable. Struct is
Well, a struct is just when you have like it's basically equivalent to a class, but all its member variables um, are public, and like there is no way to make them private, I believe.
mm-hmm. Well,
Oh, there might be a
you
way.
could.
Yeah,
I
there
think
might be a
you.
way.
I think in C++ they are like interchangeable, but like C++ doesn't have class. So in C, when you use a struct, everything is always public. But I think it's if you make it, if you added like private before like your like your field, so she said private int val, it would be private. But if you don't add anything or you add public, it'll be public. So okay, that's a good question.
Yeah.
Does anyone
And
have any?
also,
Okay.
I just want to add up to is that like like structs also don't have like the class unique features in C++ that classes do, stuff like, I don't know, subclassing, and like taking advantage of polymorphism and stuff like that. And like you would use it when you're like you don't need those features and you only need a structure, or like a union of like other data structures, and you're not looking for like creating an entire class for something.
Okay. Are we okay now? Should we keep going? Everyone's clear on what like a tree is, a binary tree. All right, I think we're good. So this is a binary tree. If it wasn't a binary tree, maybe it could be like, I don't know, like a 3 tree. We could have like a nodes that have more than two, like we would call them children. But like for the sake of like an easy implementation, we'll just use a binary tree. So a node has like a left subnode and a right subnode. Which brings us to like another definition, a binary search tree. So in a binary search tree, every node's value in like the left subtree will just, yeah, the left subtree. So if this is our root, this would be the left subtree right here. Every node's value in the left subtree is less than the root's value. And then also every node's value in the right subtree is greater than the root's value. And this is a recursive definition. So the left and right subtrees, so this tree right here and this tree right here are also binary subtrees themselves. So I have a question for you guys. It's a bit of an exercise if you're not sure on what about equal to? It depends on how you like define a binary search tree. Let's just pretend for right now that all the values of the nodes are unique, so that they can't be equal. All right, okay, that's a good question. But I have one question for you guys. If you're a bit shaky with the definition, what about this tree right here that I've been using as an example? Is this a binary search tree? Okay, I have 2 yeses. All right, 3 yeses. Okay, I think all you guys understand why this is a binary search tree. But for those of you that aren't exactly sure why this is a binary search tree, I'm gonna go over for you guys. So we have the root right here. This is like a value of 8. Everything in this subtree is less than 8. Okay, so that marks the first point. Everything in the right subtree is greater than 8. So that's point 2 knocked off. And then the left and right subtrees are binary search trees themselves. So now we got to check if this is a binary search tree. So our current value right now is 3. This is our left subtree. 1 is greater than, 1 is less than 3, so that's 0.1. 4, 6, and 7 are greater than 3, so that's 0.2. We want to check if this subtree and this subtree are also binary search trees. So this is just, 1 is just by itself. So we'll just say, okay, yes, it's a really like trivial example of like a binary search tree. And I think you guys can see from, we can just inspect this example. Yeah, this is a binary search tree because 4 is less than 6, 7 is greater than 6. But we're not done yet. We have to check this subtree. So let's see what we have here. Is this subtree is everything in this subtree is greater than 10? Everything in this subtree is less than 14, and this is definitely a binary search tree as well. So there we have it. This is how we can tell that this is a binary search tree. And so what's like the importance of binary search trees? If you guys have been going to our past presentations, we've talked about this a little. They're used to implement ordered sets and maps. So we've explained like what a set and a map is already, but if you care about the order, binary search trees are like a very good thing to use. But unfortunately, doing accesses like searches, insertions, and deletions are a little bit slower if you care about the order in the sets and the maps. So I have a little like big O table that talks about all the operations you may want to do on a tree, which is also like for using ordered sets and maps. So there we have like our access, search, insert, and delete, and they're all O log of n. Could someone here explain to me why like the runtime is O of log of n? It's just assume that n is the number of nodes inside a tree. You don't have to explain like in detail for like each one, by the way, just a general idea of why it's O of log of n. Okay. Because you kind of divide the nodes and search by 2 each time. Yep, that's basically it. If you guys are familiar with binary search, you know like the idea of, oh, you go to the middle and then like you split the array down the middle, and then you check either the left or right array, and that greatly that completely halves your runtime, and it has like a runtime of O of log of n for that. And you can basically see the same example here. So let's say we are searching for like the number 7 and we're at 8. Well, by definition of binary search tree, it can't be in the right because everything in the right is greater than 8. So it has to be in the left. So now we're here. It can't be in the left subtree because everything left is less than 3 and we're looking for 7. So it has to be down in this subtree. And then you can keep going. you can keep going, and then you eventually reach 7. If you if you were to search just all nodes at the same time, like if you were just to search each node, like go here, 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 and then keep going like that, it would take you, on average, it would take you a lot longer than if you were to use like the binary search technique. It's why we call this a binary search tree. It's like based off of binary search. So does anyone have any questions? It's definitely a lot, but it looks like everyone gets it so far. So I guess we'll just go into the next slide. And unfortunately, it's a lot of terminology. So hopefully you guys aren't falling asleep to this, but we can go over this pretty quickly because it's all pretty intuitive stuff. So a node, we've been using like the term node already, like a bunch already. It's just a single element in the tree. So 8 is a node, 6 is a node. They're all nodes. And the root, we call the root is the topmost node. So in this example, 8 is the root, I mean. We've been talking a bit about children, so that's nodes beneath n. So the children of 3 are 1 and 6. The children of 6 are 4 and 7, and 1 has no children. And then since we have defined children, then we can define parent, node directly above n. So parent of 14 is 10. Parent of 10 is 8. 8 has no parent because it's the root. Siblings of n, it's just nodes that have the same parents. One is a sibling of 6 because they both have 3 as a parent. Depth is kind of interesting. Depth is the number of edges from the root to n, so it's depth of n. So the depth of 6, we say like the depth of 6 is 2 because it takes 2 edges from the root to get to n. So you go from 8 to 3 and 3 to 6. So the depth of 6 is 2. The height is something similar. It's the depth of the deepest node. So I think you guys can see that, like from this picture, the deepest nodes are 4, 7, and 13, and their depths are 3 because it takes 3 edges to get from any of them to the root. So let's say we want to get to 4. We could go 8 to 3, 3 to 6, and then 6 to 4. So the height of this tree is 3. Wait, oh, that's a typo. It shouldn't say left, it should say leaf. A leaf is a node with no children. So the leaves here are 1, 4, 7, and 13. And we talked a little bit about subtrees. It's just a tree rooted at a node that is not a root. So we can say this is just a subtree. This is a subtree. This is also a subtree. And I think it's pretty intuitive. It's pretty intuitive, so we can just move on to talking a little bit more about subtrees. So the key to most problems is doing recursion on subtrees, but these slides were made before we decided to talk about recursion. So I'm a bit sorry for that, but this will be a good introduction to like our next presentation when we'll go over recursion. However, we won't use them today since we haven't like formally go over them. So we will be using what you guys have learned to solve the problems. So do you guys want me to go over like a little bit about recursion? It's just like reading out these. So like the basic idea for recursion. Bill, what are you thinking?
I think we'll be able to go over this next lesson. So
Okay.
We can keep it until then.
If you guys are familiar with recursion and you want like more exercise on tree problems, then we'll be going over like the non-recursive solution for them. So if you want to implement them with recursion like on your own, then that'd be great. Okay, so now we're going to go through tree traversals. So tree traversals are just the way you want to like go through all the nodes of a tree, because this is a bit of a trickier topic, because like let's consider a linked list. There's only one way to traverse a linked list. You just start from the head and you just keep going until you go to the end. But with a tree, since you have like a decision of which way you want to go, there's like many options that you have. So there's like two main options. You can either do breadth first search or BFS, or depth first search, or AKA DFS. We're gonna go over BFS first because I'd say that one's a bit more intuitive. And it's basically just traversing the tree by levels. So as you can see here, first you want to process the root. Processing just means like do whatever you want with it. Like let's say if you want to like print out like the value there, you can. If you want to like add it to like a sum, you can do that. It's a general thing for like what you want to do with your value. So first you process the root. So we start here. We process 8. Process the nodes at a depth of 1. So the nodes that are at a depth of 1, remember, are nodes that like it takes only one edge to get there. So that would be 3 and 10. So we process 3 and 10. Process nodes with a depth of 2. 1, 6, and 14 have a depth of 2. So you do 1, 6, and 14. And then you just keep doing this. You keep doing this. So then we'd have 4, 7, and 13. So basically, you're going down. You start from the root, you process it, go down one level, you process those, go down another level, and then you keep going until you're done processing the entire tree. Does anyone have an idea of how we could, like, the general idea for what we would use to implement this? It's a little bit hint. It's something you guys have recently learned about if you have been attending our workshops. Yes, good job. We use a queue to implement this. So what you would do is first, let's say you're given like the root. You're usually given like the root of a tree that you want to do something with. So we're given the root. What we'd want to do is store its children onto a queue. So we store 3 and 10 onto some queue. And then when we're done processing at a certain level, we would go into the queue, and let's say we see 3 first. So then we see 3, we put its nodes into a queue. So we have 1 and 6, process that. Then we process 10, put all of its children in the queue, so that's 14. And then keep going. Then we have 1, 6, 14, 4, 7, and 3. So whenever you hear BFS, you definitely want to think of using a queue to implement it. So that's BFS. What about DFS? DFS is there's actually 3 like main ways that you can do DFS inside this binary search tree. So it's pre-order traversal, in order, and then post-order. So pre-order traversal, I'll go over with you guys for right now, is first you want to process, it says current left right. So what exactly does that mean? Current means you want to process the current node. So let's say 8. Then you want to process the left subtree and then the right subtree. So, all right, let's just do a little run through of pre-order traversal. So process the current. that should right now is 8. Then we want to process the left, so we go down to the left subtree. And then we start doing pre-order traversal on the left subtree. So process the current, that would be 3. Go to the left subtree, do pre-order traversal on this. So you want to process the current, that would be 1. Process the left and right subtrees. There is no left and right subtree here because this is a leaf. So then you go back to here and you've processed the left subtree of 3. So now you're going to process the right subtree, and then you do that same process again. So you process current, so 6, go left subtree, 4. That's it. All we have to do for the traversal here. Then go to the right, just process 7, and then you have finished processing the entire left subtree. So then you do the same thing for the right. So you do 10, 10, try and process the left, there's nothing here. Process the right, process current, 14, process left, 13, process right, nothing here. And we have finally done in-order traversal on this tree. And in-order and post-order traversals are basically done the same way, which I think you guys can figure out. Does anyone want to do like in-order or post-order traversal? Like put their answer in chat. I'll give you guys like a second to do that. We have an answer for in order. Does someone want to do post order? Post order is a little tough. Okay, thank you. All right, we have 2 answers for post order. So, all right, good job, everyone. There was an interesting thing in the chat. Simon said, in order is always increasing, and then Ivan put in for in order 1, 3, 4, 6, 7, 8, 10, 13, 14, and I don't know if you guys noticed, but for in order, the numbers are increasing. Like they're always increasing. Is that always the case for any binary tree? Okay, let me see. Binary sorted. Yeah, okay. So it's not the case for every single binary tree. But if it's a binary search tree, then if you do in-order traversal, it'll give you the numbers in order, like in order of like, yeah, basically going like least to greatest. You guys may want to remember that for at least for this workshop. That's a hint for one of the problems. And yes, as an exercise, implement these 4 types of traversals. Let me give you a bit of a hint for the DFS ones. What would you want to use to implement DFS? I'm looking for 2 answers, by the way. How could we implement DFS? If implementing BFS required a queue, then maybe DFS would require, yes, yes, a stack. All right, good job. I said I was looking for 2 answers, but that might have been unfair. Might have been unfair to you guys since we haven't learned it yet. The second answer is recursion, and don't worry about recursion for right now. We will go over that in our next presentation, in our next workshop. So that was a lot. I think that was a lot of information for you guys. So let's give you guys a 5-minute break to, I guess, just process it all. Process it in BFS or DFS. I don't know. It's your guys' decision. Let's go. Okay, so let's move on to graphs. So graphs, another abstract data structure. And this time we don't really put any constraints on like how the data structures are arranged or like how the nodes are arranged. There's just edges between them. So, and these edges can like represent anything, like I guess like maybe a relation of some sorts that connect those nodes. So for example, we have 2 graphs right here. So then you just see there's nodes and then just edges connecting them. And let's say we'll call an undirected graph. So like there's edges that are like bidirectional, which means if there's an edge from one node to the other node, there's another edge from that node like back. And usually when you draw an undirected graph, you just draw like edges as just lines, not with arrows. This is a directed graph, so edges do have a strict direction. So let's say if if there's an edge from A to B, there's not an edge from B to A unless you explicitly give one. So if there were, we would want to draw like an arrow from B to A. So this is a directed graph. And then from there, you can also define something as a directed acyclic graph, which we'll just define it here because you'll probably see it in the future, or a DAG. So that's a directed graph where there's no cycles inside the graph. A cycle, I think, is a pretty like intuitive definition. If you could get from like one node, take like some path and get back to that same node. So if there's no cycles, then you have a directed acyclic graph. So can you guys tell, this is a directed graph, obviously. Is it a directed acyclic graph? Yes or no? Okay, we have 2 answers. There's a yes and a no. Are we gonna have a third answer to break the tie? Maybe. No, there's still a tie. Maybe, no, yes, no, other. There's more no's than yes, but unfortunately the answer is yes. This is a direct acyclic graph, unless I am like tripping out, which, okay, I'm not. All right, so we can't actually find any cycles from any node to itself. So there's A doesn't have a, oh, whoops, you thought it said cyclic. Yeah, this is a directed acyclic graph. Okay, so there's no, for every node, there's no like path that is a cycle that cycles back to it. So A, if you go to B, there's no way to get back to A. B, you could go from C, and that does not go back to B. could go to E, and you guys get it. There's no cycles in this graph, so it's a direct acyclic graph. Definitely a term that you want to remember for the future, because you get to learn some really advanced topics with it. Like, for example, if you guys don't worry if you guys don't know exactly what this is yet, but topological sort. It's been very interesting, the ICPC recently. Okay, so that's about graphs, and with any like abstract data structure, there's also ways to traverse it. And luckily, it's very similar to trees. You can do BFS, which is generally the same idea. Process the starting node. There's not really a route to like a graph, so you can start wherever. Let's just start at like the 1. So we can process this node, process nodes adjacent to the starting node. So everything adjacent is 1, is 2. Everything adjacent to 1 is 2 and 4. So we process those, process the nodes adjacent to those nodes. So process everything adjacent to 2 and 4. That would just be 3. We've already like processed 1, so we're not going to do it again. So we have 1, 2, 4, and then now we process 3. We keep going. Everything adjacent to 3 that we haven't already looked at is 5. Everything adjacent to 5 is 6 and 7. So we could just be like 1, 2, 4, 3, 5, 6, and 7. Okay. So that's a general thing for BFS. I would just give you guys the answer. To implement BFS with a graph, you also want to use a queue. It's generally the same idea, so using a queue is like the most convenient way to do it. And then there's also DFS, which, yeah. So for DFS, you'd want to process the starting node. So let's say we process 1. Wait, what does this mean? P1 node next to starting node. I'm not exactly sure what that means, but you want to go to process 1 node next to the starting. Okay, that means process. So let's say we can go over to 1 node that's like adjacent to it. So let's just go to 2. So we can process 2, and then we just keep going. So let's process something next to 2. 1 has already been processed. So we go to 3. We can process something next to 3. We can't do 2 since we've already processed that. So let's just go to, should we go to 4 or 5? What do you guys prefer? I just need something right now. 4, 5. Now we're just gonna go 4. Okay, so we're gonna go to 4. We process 4, and notice that now that we're at 4, we processed like we already processed 1. We've already processed 3. So we're not exactly done yet. We haven't processed this entire graph. So now what we're gonna do is backtrack to 3. So we go back to 3. And then we're gonna keep going, process something that we haven't seen yet. So that would be 5. We process 5. Then we want to process 6. We're not done yet. So now we want to backtrack to 5, then go to 7. Then we keep backtracking. So we go to 5, then we go to 3, then 2, 1, and then we are done. So that is a DFS like graph traversal. Does anyone have any questions for like these general types of traversals? Okay, so there's no questions. And of course, if you want to implement DFS, 2 solutions, use a stack or use recursion. Either way is like equally as good. And like as an exercise, if you want to implement them, you always can. Okay.